Yeah, thank you for having me and giving me the opportunity to talk. Today I want to talk about a class of particle smoothers and discuss some tools that can be used within this class to combat problems that are arising in the context of nonlinear and high-dimensional settings for smoothing. My collaborators on this work are Sahani Pathiraja and Sebastian Reich, we're all from the University of Potsdam. And so I'm assuming a standard model. I'm assuming that it's a Markov model from order n, because smoothing is much more effective if you have shared memory. And observations are noisy and have a nonlinear observation operator. So I'm interested in approximating the smoothing distribution. It can be the marginal or the joint smoothing density, but I'm reducing the problem to look at fixed lag smoothing, because if you look at a too large time interval, the smoother just becomes degenerate. So I'm restricting myself to a time window with a certain lag L, and I'm trying to approximate this fixed lag smoothing density. So just to, because the way I'm proposing the algorithms will be somehow in a sequential filtering way. And if you think of approximating this for L equals 0 is just the filtering density. So you can interpret the whole thing as just augmenting the state space of the filtering distribution and by the additional state vectors going back in time. So essentially, all you're doing is making your problem even more high-dimensional, assuming you're already starting off with something high-dimensional. So you're a little bit worse off, and that's why I want to look into tools that can be used in this particular setting. So everything, of course, if everything is nice and pretty and linear, we can turn to the Kalman smoother or Ensemble Kalman smoother. There are many variations. But I'm more interested in the nonlinear case where everything is not nice. And of course, there's still many things you can do. But as we've already heard in the many talks, people are still trying to figure out how to deal with the nonlinear setting. I want to look at particle methods. So I'm approximating the posterior in a Monte Carlo fashion. And depending on how you get from your prior ensemble to the posterior ensemble, you end up with a variation of different smoothers. This could go more in the particle smoother direction or more in the Ensemble Kalman smoother direction. And I will discuss a mixture of both. So yeah, I'm sure everybody knows, but just to point it out again, of course, you would like to use something like a particle filter, because you know then in the limit, at least, even in the nonlinear case, the solution, you will get the correct solution or the correct density. But the problem is in a finite setting, especially if it's high-dimensional, you have the problem that the effective sample size becomes really small really quickly, and you're actually degenerating really fast. And if you look more at Ensemble Kalman smoothers, you actually move your ensemble towards the observation, and this is somewhere making the whole thing more stable, even in a high-dimensional setting. So we kind of want to use this idea of actually moving towards the observation to not degenerate as fast in a high-dimensional setting for particle methods as well. So I want to look at the class of linear ensemble transform smoothers that are based on the idea to actually move the ensemble, and we'll move them in a linear fashion. So the general formulation is this. So this is basically the ensemble of the joint state for the window I'm looking at, conditioned on the data up to time k-1, and now we want to update to the data up to time k, and this is done in a linear fashion. So because this is a lot of notes might be fairly abstract, but I will just give 3 examples after this of classical filters you all know that fit into that setting. So why look at those? Partly because they have the idea of actually moving the ensemble towards observation. And the other reason I want to look at this particular class of smoothers is because you can employ certain tools such as localization, and you can actually have hybrid formulations. And by hybrid, in this case, I actually mean having a combination of a particle filter in the sense that it's consistent, and having something that has, for example, Gaussian assumptions and might not end up with a correct posterior density, but is somehow more stable and robust. So I want to have a mixture of those. This is what I mean by hybrid. And then I also want to talk about some adaptive spread correction, which I will approach in a moment, a matching fashion. So all of these tools can be employed for this particular family of smoothers, and that makes them kind of neat to use in a high-dimensional nonlinear setting, because all of these help. All of these tools help there. Just to give you, I'm not going to go into them. So the classical Ensemble Kalman smoother belongs to this family. Also, all ensemble square root smoothers fit in that context. And also, nonlinear ensemble transform smoothers that do actually not assume Gaussianity and are based on the idea to also match the first 2 moments, but not of the Kalman filter, but of the particle filter for a finite number of ensemble members. So they kind of, if you assume that the finite approximation of the first 2 moments of the particle filter are somehow good, then you actually achieve much better results than assuming that you're Gaussian. And then another smoother that is in this class, this one I particularly want to highlight because it's actually a consistent smoother, so you do, in the limit, end up with the correct posterior, is the ensemble transform particle smoother. It's based on the ideas of the filter version of this, which was first derived by Sebastian Reich. And the whole idea is basically you want to replace the resampling step in a particle smoother by something deterministic. And you basically want to approximate a transport map going from the prior, or the random variable associated with the prior, to the one that's associated with the posterior. And one way to approximating this for a discrete setting is to say, okay, I have a linear transformation. And this linear transformation has to fulfill certain conditions to basically make it a stochastic matrix. And there are actually several in this linear, if you want to have this linear transformation, there are actually many choices you can have. You could, for example, one of the simplest thing you can think of is just to write the weights of the particle filter in the columns of your linear transformation, which would kind of resemble monomial resampling. So discrete deterministic approximation of monomial resampling. But while this is perfectly fine, you somehow also want to, because in this case, the prior ensemble and the posterior ensemble are somehow independent. But assuming that you actually trust your model, you intuitively would want the prior and the posterior somehow to be close, or at least correlated, because you assume that the model is actually doing the right thing. And that's why you're not going for any map, you're going for a transport map that's actually minimizing the this problem here. So I will not go into details, but the whole idea here is somehow to increase the correlation between the two random variables. So the discrete version of this is this here. So you want to have to solve this optimal transport problem. And yeah, the key thing to remember is it's consistent in the limit. And yeah, and it maximizes the correlation between the prior and the posterior ensemble. Now, optimal transport problems are not easy to solve, but there are solvers out there that approximating the solution, but are still producing a good enough solution, and they're much cheaper. And another thing to point out, because I'm actually going to end up in this special case, is when you have a 1D, if your problem is one-dimensional, you can actually solve the problem by intelligent sorting. And later on, we will do localization, and then you end up in this case, and then everything becomes much cheaper as well if you have to solve this problem. So now, in this class, I now need to look into classical tools that are typically used to combat the challenges one is facing in the context of nonlinear and high-dimensional filtering. And the first thing I want to look at is, because also for this discrete approximation of the ETPF, and it's also a problem in the Ensemble Kalman filter, you're always underestimating the spread. And that's why you're doing stuff like particle rejuvenation or inflation. And this is done everywhere, but you somehow don't want to, of course you can tune it somehow that it works, but you want to do it maybe somehow that you don't just tune, but have some reasoning behind it. And here we wanted to do adaptive spread correction by saying, okay, we basically looking into moment matching, which is a typical thing done in many filters, either for the matching to the Kalman formulas or like the nonlinear ensemble transform smoothers matching to the first two moments of the particle filter. And this is exactly what we're going to do. We're going to say, okay, let's match to the second moment and assume that we already have the first moment. That, of course, rules out several filters that are in my class, because I need those two already to match. So the first moment has to already be correct. So that rules out, in the nonlinear case, filters such as the Ensemble Kalman smoother or the Ensemble square root smoother and such things. But it leaves actually the NETS and the ETPS and the, all the other ones you get when you actually solve the simpler approximation of the optimal transport problem. Since I seem to be bad when it comes to time, you do this update by actually adding, just like you would do in rejuvenation, adding a correction term. So, and let me just show you some results. It actually works really nice. It does not only improve the first two moments, but it actually also improves the other moments. And we looked at it for the longest 63. And it really, really improved also the original ETPS we had, because it also, the ETPS was the one that is consistent, and it was also significantly underestimating the spread, so those kind of tools really help, as you can see here. And you can also do an optimal rotation. Unfortunately, I cannot go into the details, but also smoothers such as the NETS can be significantly improved by using a rotation, which you can always add to this correction term. Then we looked at some models with memory, and also there the results looked really nice. And another thing is that you can do is you can now combine all kinds of filters from this class. So you can go for a mixture of like ensemble square root smoother and the consistent ETPS. And the idea is just you split the likelihood as you would do, for example, in the tempering case. And this works out really well. It's actually that even for small ensemble sizes where particle filter approximations do not do so well, you end up in the with the best results where you actually have a mixture of the two. And this is it, time-wise. Yeah. So I'm just going to finish here. So I'm not getting to localization, but it also works.